Hi everyone, I'm Rishabh and I'll be solving some problems on sequence and series. This lecture is conducted under GSHOC. So let's begin with this first problem that says find 2 squared upon 2 squared minus 1 times 3 squared upon 3 squared minus 1 times 4 squared upon 4 squared minus 1, and that goes on to 20 squared upon 20 squared minus 1. So give this problem a try for 2 minutes, and when you are done you can watch the video. Okay, let's begin. So in this problem we are required to find a telescoping product. So we can do that by, like, we should have an idea that some of the terms would definitely get cancelled and it would simplify to some small fractions and not this big scary thing. Okay, so let's begin writing the terms in a different way and use this property, that is n squared minus 1 equals to n minus 1 times n plus 1 for the denominator, and this could be simplified in this manner: 2 times 2 upon 2 minus 1 times 2 plus 1, 3 times 3 upon 3 minus 1 times 3 plus 1, 4 times 4, 4 minus 1 times 4 plus 1, that goes on to 20 times 20 upon 20 minus 1 times 20 plus 1. Now you should see that some of the terms get cancelled, like in this way: 2 gets cancelled by 3 minus 1, 3 gets cancelled by 4 minus 1, and you can see this thing, that's 2 plus 1 gets cancelled by 3, 3 plus 1 gets cancelled by 4. Similarly, this 2020 would get cancelled by 2019 plus 1, and this 2020 minus 1 would get cancelled by 2019. So everything would get cancelled. This would also get cancelled by some number, and this would also get cancelled. So we see a pattern that there are two patterns, like one number gets cancelled in this way and the other gets cancelled in this way. Okay, and the whole thing gets simplified to this thing: 2 upon 2 minus 1 times 2020 upon 2020 plus 1, which is actually 440 upon 2021. So this problem was from HMMT, and I think this problem must have helped you to understand some concepts of telescoping product. So let's move to the next problem. Now let's begin with the second problem, that is from the purple comet competition, and it says that define a recursive formula, that is a sub k equals to k square plus 1. It should be 1, and we have this thing, that's k square plus 1 times k factorial, and b sub k equals to a1 plus a2, and that goes on to a sub k. And here's another recursive formula, that is a100 upon b100 equals to m upon n, and where the GCD is given as 1 of m and n. So we need to find the difference of n and m, actually n minus m. So we can do this problem using this method. So give this problem a try for 2 to 3 minutes, and when you are done you can watch the solution. So we can write the recursive formula as ak equals to k square plus 1 times k factorial, and this could be written as k times k times k times k factorial plus k factorial. So I'm actually opening the bracket and trying to make something with k plus 1 factorial, and actually trying to make something with k plus 1 factorial and k factorial. So we add here, that's k plus 1 minus 1 times k factorial plus k factorial. So we added this one and then subtracted this one, which has zero effect on this recursive formula. And then we can write this thing, that is k times k plus 1 factorial. Actually, let me write one more step, k plus 1 times k factorial minus of k factorial plus k factorial, and then this boils down to k times k plus 1 factorial minus of k times k factorial plus k factorial, and this is k times k plus 1 factorial minus of actually this would be minus k factorial k minus 1. Okay, that makes sense. Now see what you can do in this factorial thing. If you write bk, we have another recursive formula, that is b sub k equals to a1 plus a2 dot 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 plus a sub k, which you can see here. It's given here. And now try writing these things in different manner. What I mean to say is that you can rewrite this as 1 times 2 factorial minus 1 factorial times 0 from this thing. So let me highlight this. So we have this relation. Okay, let me just underline this. From this we can write this thing, and this would simplify to this thing, that is plus of 2 times 3 factorial minus 2 factorial times 1 plus 3 times 4 factorial minus 3 factorial times 2, and that goes on to actually this thing, that is k times k plus 1 factorial minus k factorial times k minus 1. So this thing gets cancelled, and then we have this thing. So this would also get cancelled, and then this would also get cancelled by some term, and this negative would also get cancelled by some other term. So we would be only left with k, that is b sub k would be equals to k times k plus 1 factorial minus 1 factorial times 0, but this quantity is already equals to 0. So this can be rewritten as b sub k equals to k times k plus 1 factorial. And now we were given another relation, that was a sub 100 upon b sub 100 equals to m by n. So we found this thing, that was a sub k. So a sub k was k times k plus 1 factorial minus k factorial times k minus 1, or this thing, that was k square plus 1 times k factorial. So let me rewrite an equation for ak upon bk. So this would be a sub k upon b sub k, that would be k square plus 1 times k factorial upon, and bk was k times k plus 1 factorial. So this could be written as k square plus 1 times k factorial, and the below one denominator would be k times k plus 1 times k factorial, and this would get cancelled. So it will be left with k square plus 1 upon k square plus k, and hence a sub 100 upon b sub 100 would be 100 square plus 1 upon 100 square plus 100. So this is your answer, and you could find it was given as, so let me see this again. It was given to this is actually equals to m by n form, and now let's see. So we were required to find n minus m, therefore n minus m would be 99. So this must have gave you some idea how to solve such kinds of problem. So the main takeaway from here would be to add some plus 1 minus 1 to make it of the form k plus 1 factorial, and try to use that. Okay, so I'll give some more time to watch this solution, and then we'll move to the next problem. Okay, now let's move to the next problem. That is, prove that if a, b, c, d are 4 consecutive terms in a geometric sequence, then they are related as this. So I won't be solving this completely, but I would give an idea, like I'll give a hint only for this problem. So solve for LHS using a equals to a, b equals to ar, c equals to a times r squared, and d equals to a times r cubed, and then just sub in these values and you'll get the thing. There also exists a easy way, but I think this should make sense, and this is a pretty easy problem, so I won't be going over the complete solution. Okay, I'll give some more time to think about this, and then we'll move to the next problem. Okay, now let's move to the next problem. So this problem is from HMMT 2003. So it says find this value. Okay, so whenever we have this kind of terms and series, so what we do is we follow a general practice that we try to write a general term. So what you can do is find t sub n, that is the general term. Okay, let me write this. And then this would be nothing but 1 upon n plus 2 squared plus n. because for the first term this is n plus 1, that is 1 plus 2, that is 3 squared plus 1, and similarly for others as well. This could be simplified to 1 upon n squared plus 4n plus 4 plus n, and then we can club the terms with variable n, and it would be n squared plus 5n plus 4, and you can factorize this thing, and it would become n plus 4 times n plus 1, and now this term would start telescoping, so this would become n plus 4 minus of n plus 1 upon n plus 4 times n plus 1. So something like this, because you want to make the upper thing to be 1, so you divide by 3, and then you can take the individual LCM, like take the terms individual and then cancel out the terms. So this would be 1 upon 3 times 1 upon n plus 1 minus 1 upon n plus 4. Okay, so we have this telescoping sum. So now start subbing in the values. That would be 1 by 3 times 1 upon 2 minus 1 by 5 plus 1 by 3 minus 1 by 6 plus 1 by 4 minus 1 by 7, and that goes on. So we can see that actually let me write some more terms so that is easier to observe. 1 by 5 minus 1 by 8 plus 1 by 6 minus 1 by 9, and then goes on. So this term would get cancelled with this, and this would get cancelled with this. Similarly, everything like this would get cancelled, and then minus 1 by 8 would also get cancelled, this would also get cancelled, but these three terms would remain. That is 1 by 2. Okay, let me use some other pen. That is 1 by 2, 1 by 3 and 1 by 4. So they would remain. Hence we can write it as this: 1 by 3 times 1 by 2 plus 1 by 3 plus 1 by 4, and you can simplify this to 1 by 3, this would be 12, this would be 6 plus 4 plus 3, and that would be 13 by 36. So I think that's right. And okay, so this must have given you some idea about how to use telescoping sum with general term. Okay, we'll move to the next problem, and for the next problem, give this problem a try for 2 to 3 minutes, and then you can watch the solution. So it says that a is less than b is less than c are three positive integers such that abc is an arithmetic progression and acb is a geometric progression, and we need to find the smallest possible value of c. Okay, so it's given that abc are in ap and acb are in gp. So the relation that we can write is 2b equals to a plus c, and c squared is equals to ab. This is the second relation. Now we need to use this equation. We will try to use this equation, and let's see how we do use it. So we can write the first equation as 2b minus of a equals to c, and then it will get simplified, and then we can actually square it, so it would become 4b squared plus a squared minus 4ab equals to c squared. So now you can substitute c squared as ab, so that would become 4b squared plus a squared minus 4ab equals to ab, and this would become 4b squared minus 5ab plus a squared equals to 0. And then you can factor out the terms, so this would be 4b squared minus 4ab minus ab plus a squared equals to 0. Hence we can factor out these terms. That would be 4b b minus a b minus a equals to 0. So b minus a times 4b minus a equals to 0. So we got two things from here, that either b is equals to a or a is equals to b, a equals to b or 4b equals to a. But it was given in the problem that a is less than b is less than c, so this would get rejected. Since a less than b less than c, now we are left with only this condition, that is 4b equals to a. Hence we can write the AP as 4b comma b. Since the general common difference is minus 3b, so c would be minus 2b. Okay, so for this to be true, since it was given a is less than b is less than c, for it to be true, we definitely need b less than 0, otherwise it won't be true, so that the terms can increase. So minus 2, so b is a negative value, and if b decreases very much, so c would also decrease very much. So okay, c would increase very much, sorry. So we need to find the smallest possible value, so b must be the largest negative value. Therefore c is equals to minus 2b, and for c to be minimum, okay, let me write one more, c minimum should be minus 2 times minus 1, and c would be equals to 2. Okay, so here's it. So this was our problem from AMC 2LA 2014, and we did solve this in this way. Okay, now let's move to the next problem. This is from the AME 1989. So give this problem a try for 2 to 3 minutes, and then we will watch the solution. So let's begin with the solution now. So it says that if the integer k is added to each of these numbers, one obtains squares of 3 consecutive terms of an AP. So we need to find k. Okay, so let's begin by writing the terms. So we add 36 plus k, 300 plus k equals, and 596 plus k. Okay, so now it says that one obtains squares of 3 consecutive terms of an AP. So what can we do? So this would be some a squared, this would be a plus d squared, and this would be some a plus 2d squared. Okay, so now what we can do is rewrite this term as, okay, so this would be a squared, and this would be a squared plus 2ad plus d squared, and this would be a squared plus 4ad plus d squared. So actually we can write this as 280 plus d squared equals to 290, actually 274. Okay, let me check. 264. This would be first equation, and actually this is 4d squared, and the second equation that we can get is 2ad plus 3d squared equals to 596 plus k minus 300. That would be 296. Second equation, now we can subtract them. Let me subtract the first one, and then we'll have 2d squared equals to 296 minus 264, 32. Therefore d squared is equals to 16, and d is equals to plus or minus 4. So we take d to be plus 4 because we know it's an increasing increasing AP. So d must be positive, otherwise it would be less. As, let me write this as k is a positive integer. Now you can sub this value here, and you can find the value of a. So 2a times 4 plus 16 equals 264. Now you can find the value 264 minus 16 divided by 8. So a would be 31. Therefore a is equals to 31, and 36 plus k was equals to a squared, that was 31 squared, and 31 squared is equals to 961, I guess. Yeah, that's equals to 961. Hence k is equals to 961 minus 36, and that is equals to 925. So you get this value. As this is from 1989 AIME, it was a bit easy, but recently AIME problems have become harder and harder. So this was from 1989, and I think you must have understood this. Okay, now let's move to the next problem. So it's based on recurrence relation. So give this problem a try, and when you are done you can watch the solution. I'm writing the terms here. Okay, so now I have written down this equation that was given in the problem, and now let's try to solve this. So think about it for a minute, and then we can begin solving this. So here's an idea. We try to divide by an minus 1 and multiply, actually only divide by an minus 1. So this would become this, that would be let's first rewrite this equation. That would be an minus 1 plus an minus 2 equals to an squared, an minus 1 squared upon an, and this would be actually equal to this 1 by n plus an minus 2 upon an minus 1 equals to an minus 1 upon an. And rewriting this, it would be equals to an minus 1 upon an minus of an minus 2 an minus 1 equals to 1 upon n. And now we can try writing the first starting terms. So we would get a2 upon a1, actually a2 upon a3, minus a1 upon a2 equals to 1 by 3, a3 by a4 minus a2 by a3 equals to 1 by 4, a4 by a5 minus a3 by a4 equals to 1 by 5, and that goes on for till an minus 1 upon a sub n minus a sub n minus 2 upon a sub n minus 1 equals to 1 by n. So you can see when you add all of these terms, these things would get cancelled. This would get cancelled with this, and the last one would also get cancelled by some term does. So we would get this equation, that would be, so I'm writing it here. Okay, now let's write the term. So it would be an minus 1 upon an minus of 1 by 2017, because it was given that a2 is, so let me write this thing, a2 minus a1 upon a2, so an minus a2 upon a1 upon a2, sorry, yeah, that would be 1 by 2 plus, actually 1 by 3 I guess, yeah, 1 by 3 plus 1 by 4 dot 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 plus 1 by 2017, actually n, let's only write n. So an minus 1 upon an would be 1 by 3 plus 1 by 4 dot 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 plus 1 by n plus 1 by 2017, that is this thing. And now we can see that an minus 1 upon an would be greater than 1 for n greater than equals to 7. Why? Because you can try writing this, some of the fewer terms, like 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7. So this would be 0.33 0.25, 0.20, and this would be 0.167. Yeah, around that. So this would give around 0.45, and when you add 0.33 it would be 0.8, around 0.8, actually that's 0.45 plus 0.33, that's 0.78, and when you add this thing it would be near about 1 but less than 1, and when you add 1 by 7 it would definitely be greater than 1. Therefore we can write it as this thing: A6 greater than A7, A7 greater than A8, and A8 is greater than A9. That goes on. Hence we can write it as A6 greater than A7 greater than A8 greater than A9, which goes on. Also it would be like A6 would also be greater than A5. You can actually see by writing the terms, so I'll just write it. So A5 is less than A6, A4 is less than A5, and A3 is less than A4. Similarly, A2 would be A2 would be greater than A1, and you can write it as A6 greater than A5 greater than A4 greater than A3 ... So in both the cases A6 is the greatest. Actually this now you can see. So in both these cases A6 is the greatest value. Now let's see the options. What options have we got? So we have these options. So A5 is the greatest term. That's a wrong option. We have A6 is the greatest term of the sequence. Yes, that's true. AM is less than AM minus 1 holds true for M equals 6, 7, 8. No, it doesn't. We saw that M should be greater than equals to 7. So option D must be right. So this is a multiple correct option. So B and D are the right ones. Okay, I'll let you think about this problem for some more time, and then we can move to the next problem. Okay, you can see the process here. So the main idea was to divide by an minus 1, and then you can do easily. Now let's move to the next problem. Think about this problem for like 5 to 6 minutes, and then you can watch the video to see its solution, as this is a hard one, so it will take time to do this one. So let's begin solving it. So you must have read the problem statement. So we are given this recurrence relation, and we need to find which of these options are correct. So it could be single correct or multiple correct. I don't know if it's single or multiple correct, but let's solve and see which options are the correct ones. So let me write by, so we can define this thing as we are given this. An equals to n plus 1 upon n minus 1 times a1 plus a2 plus till an minus 1. So we can define this as Sn minus 1. So we define this as Sn minus 1, and then we can write Sn minus 1 as n minus 1 upon n plus 1 times a sub n. Okay, so that should make sense how we can write this. What we can do is we can write S sub n as n upon n plus 2 times of a sub n plus 1. And we have one more thing, that is Sn minus 1, that's actually equals to a sub n. And how I did this was this way, that's a1 plus a2 till an minus of a1 plus a2 till an minus 1, as we define Sn minus 1 to be terms of a1 plus a2 plus a3 till an minus 1, and Sn as a1 plus a2 plus a3 till an. So that should make sense, but we can also see Sn minus 1 from here, and that would be equal to, so we can write this as an equals to n upon n plus 2 times an plus 1 minus n minus 1 upon n plus 1 an. Now let's club the an term and an plus 1. So we will get an times 1 plus n minus 1 upon n plus 1 equals to n upon n plus 2 times an plus 1, and this could be written as 2n times an upon n plus 1 equals to n upon n plus 2 an plus 1. Therefore an plus 1 would be equals to 2 times n plus 2, as this would get cancelled, upon n plus 1 times an, and hence an could be written as 2 times n plus 1 upon n times an minus 1, and an minus 1 could be written as 2 times n upon n minus 1 times an minus 2, and an in the terms, okay, so sorry about that, I was not doing, the screen isn't moving, so you could see the terms now. Okay, so now we can write an in terms of an minus 2. So an in terms of n minus 2 would be 2 times n plus 1 upon n, and we substitute the value of an minus 1 here. That would be equals to 2 times n upon n minus 1 times an minus 2. So actually that's equals to 2 squared n plus 1 upon, so we can cancel this, upon n minus 1 times an minus 2, and this could be rewritten as this thing, two cube times n plus 1 upon n minus 2 an minus 3. So we see a pattern here. So a general term could be written it in this manner, that is an equals to 2 to the power of n minus 1 times n plus 1 n plus 1 upon n minus, oh, so that would be a1. So here it would be 2, since we are increasing 1 in the denominator always. So that's equals to 2 to the power n minus 1 times n plus 1. Hence we can now find all the values. So therefore a sub 2016 would be equals to 2 to the power 2015 times 2017, as we were required to find the value of a 2016 from here, from this thing, a 2016. So now we can write this as a 2016 upon 2 to the power 2016 equals to 2017 by 2. So this is nothing but, actually let me write this, is greatest integer function. So it gives the integer value for some function inside it. So we get a 2016 upon 2 to the power 2016 equals to, so that would be 1008.5, and that would be equals to 1008. And now what you can do, we were asked to also find about this thing. So we were asked to find if this is divisible by 2019, 2 to the power 2019. So we can find the value of a 2015, and that would be equals to 2 to the power 2014 times 2016, and 2016 is divisible by 32, that is 2 to the power 5. Hence 2 to the power 2019 must divide a 2015, and you can prove the last one as well from this thing. That was Sn minus Sn minus 1 equals to, that was An. So you can find this as well, the sum of 8 terms, that was a1, a2, a3 till an. For this to be true, n must be greater than 8, and this is actually true. So I'm letting that as an exercise to you to solve that. So the correct options are A, C and D. So that must have helped you to understand something about recurrence relations and how you solve them. So I'll give you some time to think about it, and we'll move to the next problem. Okay, so let's move to the next problem, that is from the Mandelbrot competition, and it says that you need to find the sum of this, and here it's not some AGP or GP or something like that. Here it's given the general term as this. So the general term is f sub n 3 to power n, where we call fn as a Fibonacci number, which is f of n equals to f of n minus 1 plus f of n minus 2. So it's sum of two consecutive numbers which are less than f of n, f sub n. Okay, so give this problem a try, and when you are done you can watch the solution. So let's begin solving this problem. Actually we'll try to use the concept of, so I'll give you a hint. Try to use the concept of to find sum of infinite GP. Infinite geometric progression. So if you want you can pause the video and try this problem. So I'll write this: S equals to 1 by 3 plus 1 by 9 plus 1 by 2 by 27 actually. 2 by 27 plus 3 by 81 plus 5 by 243, and then it goes on, and then we can multiply 1 by 3 to this s and shift the term to 1 right. So this term would become 1 by 9, and this term would become 1 by 27. This term would become 2 by 81. This term would become 3 by 243, and let me write some more terms here. 8 by 729 plus another term would be like 13 by 3 to power 7, and here it would be 5 upon 729 plus 8 upon 3 to power 7, and it goes on. And so this became this became this, and now we take the difference. So this would become 2s by 3 equals to 1 by 3 plus this would cancel out. This would become 1 by 27 plus 1 by 81 plus 2 by 243 plus 3 by 729 plus 3 by that's 5 by 3 to power 7. But actually we have seen this term, so you can actually think, and it would be equals to 1 by 3 plus, if you take 1 by 9 as common, so you'd see where have you seen this term, and this becomes 2 by 27 plus 3 by that's 3 by 81 dot dot dot, and it's actually s. Therefore you can write this whole term as s, and it would be 2s by 3 minus let's write this 2s equals to 1 plus 3 plus s by 9. Therefore you can write 2s by 3 minus s by 9 equals to 1 by 3, and this would be equals to s equals to, that would be 3 by 5. Yeah, So this is our final answer for S. So this must have helped you understand about the Fibonacci numbers and geometric sequence. So it was a very interesting problem, and I also spent some time about thinking about this problem. Okay, so let's move to the final problem, that is from the Online Math Open 2013. So give this problem a try, and when you are done you can watch the solution. Okay, so let's begin solving this problem. So first of all, what we can do is rewrite these two equations, that is these two equations. So you should read the problem and then try to rewrite this equation as this thing, that is an minus 1 equals to 1 by 63 root 2n plus 2. And similarly we can write bn plus bn minus 1 equals to 1 by 96 root 2n plus 2, and then you can multiply these terms to find something of this form. So let's actually do that. So we multiply and we get an bn plus an bn minus 1 minus an minus 1 bn minus an minus 1 bn minus 1, that is equals to 2 times n plus 1 upon 63 times 96, and that would be equals to n plus 1 upon 63 times 48. That should make sense. And now we can take summation individually. So we can club these terms. So this would get clubbed with this, and this gets clubbed with this. So we can write this an bn minus an minus 1 bn minus 1 plus an minus 1 bn minus an minus 1 bn equals to n plus 1 upon 63 times 48. Now what you can do is take summation. This could be summation from, so we are required to find the summation from k equals to 1 to 2013. So take this summation as n equals 1 to 2013, and this as summation n equals to 1 to 2013. Let me write summation more clearly. And this would also be summation n equals to 1 to 2013. Now it's just a bunch of things to do, so you just need to calculate. This is of the form, so let's first write the first few terms of this thing. So it would be a1 b1 minus a0 b0 plus a2 b2 minus a1 b1 dot 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 till a 2013 B 2013 minus A 2012 B 2012. So this all terms would get cancelled, that is A1 B1 A2 A this would get cancelled with this would get cancelled with some other term, and this would also get cancelled. So we will be left with A 2013 B 2013 minus A0 B0. So we get this from this summation. Okay, let me change the color. Okay, so that should be fine. And now we need to find what we get from this equation, but we are required to find this thing. Okay, so I'll just let this whole equation as let this whole summation as some big X, as we are required to find this big X. So I just wrote big X, and this thing summation n equals to 1 to 2013 n plus 1 upon 63 times 48. So you can write this as 1 by 63 times 48, 2 plus 3 plus dot 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 plus, actually you can write in this way, 1 plus 2 plus till 2013, and this thing. Oh, my pen is not working. Give me some moment. Okay, so it will take time for the pen to charge, so give me some 2 to 3 minutes. Okay, so let's begin solving this again. Plus 2013 upon 63 times 48. So I just split these terms and then I did the calculation, and you can write this as 1 by 63 times 48, 2013 times 2014 by 2 plus 2013, and let's see what happens with this one. It was given in the problem that A 2013 is equals to B0 and B A0 is equals to B 2013. So this is nothing but 0. So if you have doubt, then you can ask in the comment sections and I'll just clear them. So we wrote it from here. That was A0 equals to B 2013 and B0 equals to A 2013. And now we have finally left to calculate this. That is 1 by 63 times 48 times 2013. We take the 2013 as common, and that's equals times 1008. So let me calculate this, and it would be equals to, okay, let me check my calculations again. So we take this common, and 2014 by 2 would be 1007. So that would be 2013 times 1008 upon 63 times 48, and I think that's right. So you can calculate this and get your answer. So it isn't a big deal to calculate that, but that's all I have to tell you about sequence and series. And if you have any doubt, you can ask it in the comment section. And I think this was problem 25, I guess. Not sure about the problem number, but it was in the range of problem 25 to 30, but I'm not sure. Okay, so let's end the video, and thank you for watching the solutions, and hope this problem must have helped you.